Hi kids, this is the first lecture in the series on wave-particle duality, called wave-particle duality or mass-energy equivalence, which is another way of basically saying this, this simultaneously existing conflicting idea that we're going to be dealing with a little bit later on. Okay, so let's start by talking about what do we know about waves and particles. Waves in your old physics classes are traditionally defined as energy moving through space, no matter what kind of wave we're talking about. We don't tend to think of waves as having any kind of mass or gravitational interaction with other waves, right? There's no, like, the sound waves that I yell don't have any gravity, or light doesn't pull us itself or hit us, when you tend to think of, like, you walk out in the sunshine, doesn't whack you in the face. And we tend to use the idea of conservation of energy to think about the interactions between waves for interference and what happens when two waves exist in the same place at the same time. They can pass right through each other. We don't lose energy, so we tend to use energy when we think about waves. Particles, on the other hand, are things, tiny little balls of matter, and we tend to think of them as having mass, obviously, and being subject to gravitational interactions with each other. They can attract or well, they don't repel each other from gravity, but they can attract each other via gravity. We use classical physics, mechanics, Newton's laws, forces, and velocity, acceleration, that kind of stuff to describe the motion and movement of particles. And typically, we tend to use the other conservation principles, conservation of mass and momentum, to dictate the interactions between particles. So conservation of mass basically says if I take a pencil and break it in half, well, now I can add up the mass of the two halves and I'm still going to have the total mass there. Conservation of momentum says that an object moving will continue moving with the same momentum unless it transfers momentum to another object. If you took AP Physics C, you probably learned about that. In this class, it's not as big of a deal, but that tends to be a way we use particles. Unfortunately or fortunately, physicists have discovered that light does all of these things. So I don't know if you guys can see that illusion there, but depending on how you look at that, you can see light as a wave or you can see light as a particle. And the truth is light exists simultaneously as both of those states, which is what we're going to be talking about in this video. So the first kind of inkling that something funky might be going on with light that we were going to have to handle in physicists was when Albert Einstein derived an equation that is extremely famous, known as, well, it's one of the equations in his paper on special relativity, and it's E equals mc squared. So, this is the, if you ask an intro physics student what physics equations they know, this is the one they know, but we don't talk about it in freshman class. We don't talk about it until now. So this is the moment when this equation really becomes relevant. If you think about it, this equation actually has two sides. The left side, energy, is like the wave energy side, right? So we're talking about waves, which are by definition energy. And so that all is encompassed in this idea of energy. But the other side you can think of as the particle and mass side, right? Because we have little balls of matter. And this equation says that they're actually the same thing. And so that explains a little bit why we notice these properties overlapping when we talk about light, because you can convert back and forth between waves and energy, or between energy, which is waves, and mass using this equation. A note about this, obviously, c is the speed of light in a vacuum, which is 3 times 10 to the 8th. It's a huge, huge value, and that has many implications when it comes to dealing with this equation. So a few other ramifications or things that fall out of this equation. In the past, we've been talking about conservation of mass and conservation of energy as separate entities. It turns out they are the same thing. If you can convert back and forth between them, they are fundamentally the same thing. And physicists refer to this as mass energy. And mass energy is one of the fundamental properties of the universe that is conserved, along with momentum, angular momentum, and charge and spin. The last one is actually this big thing that includes mass and energy all together. And that means that they are conserved together. So you can convert one into the other without violating any principles of physics now that we have this equation. However, because that constant c is such a huge value, this means that teeny tiny amounts of mass turn into enormous amounts of energy. And people tend to think that they're seeing this on a daily basis around us. No, this kind of thing, this conversion of mass into energy, only happens certain places like inside of stars and nuclear reactors, this is not something you're witnessing on a normal daily basis. Like if you burn a fire and it looks like the logs have gone away, it's not because they've turned into energy, because the amount of energy you would create out of a log would explode this universe pretty much. So that is, the mass is staying there, it's turning into other forms of matter, but this conversion only happens in really special scenarios, including fission, nuclear reactors, and then the other option, and fusion. And we'll be talking about those kind of at the very end of this unit. So this is an example of a conversion from mass into energy. We have an atom that changes form, turns into a slightly different version of itself that loses some mass, and that sends out gamma rays, which are examples of light energy, typically. And then the other side of this is that, if you are trying to create mass, you need an enormous amount of energy to create a relatively tiny amount of mass. So like the Big Bang happened, they tend to think of the Big Bang as, energy, a ton of energy being stored in a really tiny location. But if you imagine how much energy was required to create all of the mass of the universe, given this conversion is an incredible amount of energy in the Big Bang, like almost unfathomable amount of energy. There is one little funny implication that I found. Some people, as we start being interested in interstellar travel and going to other planets, and people think, just go faster, just, keep propelling stuff, shooting gas out the back of the spaceship. There's no friction, so the spaceship should be able to go faster and faster and faster until we can finally reach the speed of light. Like, why can't we go past the speed of light? And the answer is because since mass and energy have this equivalence, at some level, as you start approaching the speed of light, you can see in this diagram down here, as you start getting closer to this 1.0 c, additional thrust actually doesn't add to your velocity, it starts adding to your mass instead, because you're gaining energy, you're gaining kinetic energy, but kinetic energy and mass sort of blur together at really high speeds. And so consequently, you get heavier, and then you can't accelerate yourself more because the amount of force that would be required to accelerate a heavier object becomes infinite. So that is one of the technical challenges of interstellar travel. There are plenty of examples of, and so if we're going to say that mass and energy are equivalent, that's not, there are places where we see this more commonly. Some masses and some waves are more prone to exhibiting both of these properties at once. Like you don't really normally see the wave property of this calculator, even though it does exist. And so I want to talk a little bit about where in the actual universe do we see waves exhibiting particle properties and vice versa. So classical waves, like typically we see this on the order of magnitude of light photons, can act like a particle at times. One of the things you'll be learning about in a future slideshow is something called the photoelectric effect. But remember how I said when you stand out in a beam of light, you go out in the sunlight and you don't get whacked over? Well, actually, that's not true. Things actually can get hit by a beam of sunlight and gain the momentum from that sunlight. So those things that tend to respond to this amount of momentum that light can transfer is electrons. So this is actually the foundational bit of why solar panels work, is that light comes in and uses its momentum to hit electrons and force them to move through a circuit, which is kind of cool. Another time that we notice this is in nuclear decay, which you may have covered in a chemistry class. But the idea is that when a gamma ray hits something, or when a particle explodes via nuclear decay, when it divides into daughter particles, if one of them goes off in one direction, the other one goes off in the other direction, or the light can even push that particle around a little bit. So momentum is conserved when a particle splits in two or more particles, even if one of those particles is a photon, which is a piece of light. So we still conserve momentum, even if one of the parts is actually just light. There are other places in this universe where we notice particles exerting wave properties. Typically things like very, very, like I said, we don't see it very often with this, and I'll talk about why in a couple more slideshows from now. But we do see it on very tiny things like subatomic particles or electrons acting like waves at times. So for example, subatomic particles can actually undergo constructive or destructive interference. This is a photograph from what's known as a scanning electron microscope, and you've probably heard of those things before. My husband actually helps build those things at a company out in Hillsboro. And I always thought that the way an electron microscope was that it fired electrons at things, and those electrons bounced off the things just like particles, and then we somehow caught the electrons on the other side and figured out what the things looked like based on the electrons bouncing off of them. It turns out it's not that at all. It's actually firing the electrons through them and using the wave properties of the electrons instead of the particle properties. So we're not actually catching them. We're actually looking at the pattern created as those electrons act like waves when they go through the particle. So kind of a cool little application of this. A second example is something known as diffraction. And again, we're going to cover this in a later slideshow, but imagine shooting something at these two slits in the screen. You would expect if an electron was a tiny piece of matter, like a little bouncy ball, that it would go through those slits and it would make two stripes on that screen. But what we actually see is electrons make a whole bunch of bands, which is what you would see if electrons were actually waves. So we get some really interesting results in diffractions. So subatomic particles, the only way that we can explain this in physics is that those electrons are actually passing through multiple slits simultaneously. So the electron somehow turns into a wave and then back into a ball of matter as it passes through. And there's a fun video to watch if you want to see the kind of mind-altering conclusions that are drawn based on our experiments. Speaking of particles acting like waves, there is an equation on your equation sheet known as the de Broglie wave equation. The big idea is that particles, solid objects, you can actually calculate the wavelength and frequency of those particles, and then you can treat them just like waves in any of your equations or your analyses. This equation comes from an algebraic combination of E equals mc squared, the wave equation, and then the definition of momentum, which we didn't talk a lot about in this class, but that's P equals mass times velocity. And this is the way the equation looks on your equation sheet. So in that equation, the wavelength, lambda, is specifically the wavelength of a particle. So you would never use this equation if you were talking about something like visible light wave. You wouldn't use it on any kind of classical wave. You can only use this to find the wavelength of what you would tend to think of as a solid object with mass that's moving. The h in this equation is known as Planck's constant, and we'll be talking more about that in a future video. On your equation sheet that's in the constant section, you should note that there are two different units available depending on the kind of problem you're solving. But for this equation, for the de Broglie wave theory equation, you're always going to use the Joule-second equation because you want to end up with a wavelength that is in meters. The P in this equation is momentum. The equation for momentum is the mass in kilograms multiplied by the velocity in meters every second of a particle. Just a little visual, which is kind of neat to show that when you send X-rays, which are classic waves, through aluminum foil, you get this interesting pattern known as a diffraction pattern, which again we'll talk about in later videos. But you get a very similar pattern when you shoot electrons through the foil, showing that those electrons are actually interfering as a wave, and you would use the wave, this de Broglie wave theory equation, to do the math that would explain why it does that. Sometimes problems using that de Broglie wave equation pop up on the exam. Sample problem would be something pretty straightforward that basically says find the de Broglie wavelength of a beam of electrons at 0.4 C. So, there's a bunch of clues in that problem that tells you this is the equation to be using. Number one, they specifically ask for the de Broglie wavelength, and that tells me we're talking about the wavelength of a particle. And the second thing is, like, we're asked to find the wavelength of something you wouldn't normally think of as being a wave. In order to solve this problem, there actually are three constants that you'll need. H from the equation sheet in joules, which is Planck's constant. You need to remember the speed of light in a vacuum is a constant, so 3 times 10 to the 8th, and that's on your equation sheet as well. And you'd also need the mass of an electron, which is also on your equation sheet. So I'm going to ask you to pause the video if you want to and try solving this problem, and then start it back up again in a minute to see if your solution matches mine. Okay. So I just used the de Broglie equation here. I'm just going to plug in wavelength is equal to h times 0.4 times 3 times 10 to the 8th times mass of an electron. I should have written those all as variables, but anyway, it's just straightforward as plugging those those four things into your calculator, and I arrived at a solution of 6.01 times 10 to the negative 12th meters for the wavelength of an electron, which is very, very small, but not so small that it's like out of the range of reality. Okay, there are waves that we deal with that are that small. So electrons consequently frequently act like waves. You could also have a problem that asks you to find your de Broglie wavelength when you're running at top speed, say 7 meters every second. In this case, you're going to do the same process. Wavelength equals h divided by your mass, which is roughly 50 or 60 kilograms, times your velocity, which is roughly 7 meters every second. When you plug in those things, you're going to arrive at a wavelength for yourself at about 2 times 10 to the negative 36 meter. And that is infinitesimally small. It is not a number that is sort of in the realm or range of anything that we sort of observe in this human world, which is why people don't tend to act, you don't notice people's wave properties very often, even though they might theoretically exist, because we have so much mass and because our velocity is so slow compared to other particles. The last thing in this sort of intro video of like, what are we going to be covering in this unit to some extent, is something known as quantum uncertainty. You have perhaps heard of the Heisenberg uncertainty principle as an abstract thing, but specifically relevant to this class, it says that the more accurately we measure the frequency of a wave, the less accurately we can measure its location in space and vice versa. Implications of this are really weird. Basically, the act of measuring things interferes with the objects themselves. So you're not just an objective measurer. You tend to think of like taking a meter stick and measuring your shoe, for example, doesn't change the shoe. But at the quantum level, trying to see it, because the only way we can measure things is through waves, really. We use the light waves to measure the location of the shoe. The only way to measure things is by somehow interfering or interacting with their waves. So the more we measure them, the more we've actually changed them fundamentally, which is kind of interesting. On the AP2 exam, sometimes you get pictures that kind of look like these things on the right. And these are showing how this is kind of a wave representation of a photon, a tiny little ball of light. And over here you can see like this is the position or the location of the photon. So you're pretty sure you know where that photon is. It's a pretty small location. That distance of the photon is pretty small, so pretty well defined. However, this side is the wave number or the wavelength, and the better we can determine the location, the more wide the range of possible wavelengths is. So the more we know about the location of a piece of light, the less we know about what its wavelength is, and vice versa. Down here, we don't really know where this thing is, right? It's really spread out and stretched out, but what we can say with some accuracy is that we know what the wavelength is because there's a much higher probability of existing at a certain location. So for the test, the more certain you are of a wave's position, the less certain you are of its wavelength, and that is all coming out of quantum uncertainty. Okay, so that's the end of this video. I'm going to, this was just sort of a preview video of all the topics that are covered in this unit, so hopefully this gave you an idea of what's coming up.